By now, you've probably heard the news. An interstellar comet is passing through our solar system, 3I Atlas, the third object from beyond our solar system ever detected by humanity, and it's heading straight for the sun. But here's what most headlines miss. We're in the middle of something extraordinary right now. This isn't a discovery that happened and then finished. This is an ongoing event, a cosmic encounter unfolding in real time, and astronomers around the world are frantically collecting data before this ancient visitor disappears forever. So what do we actually know about 3I Atlas so far? Where did it come from? What is it made of? How big is it really? Why is it losing water at such an alarming rate? And perhaps most crucially, what does this tell us about the universe we actually live in? In this video, we're breaking down everything we've learned about this interstellar object, from its discovery in July to its current approach toward the sun. We're separating the facts from the speculation. We're exploring the mysteries that remain unsolved, and we're asking the questions that scientists still can't quite answer, because 3I Atlas won't be here for long. By the end of the year, it will have passed the sun and begun its journey back into the darkness. This is our window. This is our moment to understand. So let's dive in and see what we've actually discovered about this visitor from the stars. But before we begin, if you'd like to support the channel, please take a moment to like and subscribe. I can't thank you enough for your support. And also, I'd love to know where you're tuning from and what time it is there. It makes me so happy to see how these videos connect people from around the world. Now, settle in and let's dive in. Something knocked on our door. Not literally, but something vast and ancient, something that shouldn't be here, has arrived at the threshold of our solar system, and we're only just beginning to understand what it means. On July 1st, 2025, a telescope in the mountains of Chile, scanning the night sky as it has done countless times before, detected something unusual. Not a new discovery in the traditional sense, something far stranger, something that came from outside, from the deep, cold nothing between the stars, from a place so distant that our minds struggle to comprehend it. This object has a name now: 3I Atlas. The Roman numeral 3 tells us something crucial. This is only the third of its kind ever detected by humanity. The letter I stands for interstellar. Atlas is the name of the telescope that first saw it clearly, though it had been there all along, hidden in old photographs in archives, waiting to be noticed. Observations from June 14th, 2025 have since been unearthed, pre-discovery images. The comet had already begun its journey toward us before we even knew to look. But here's what matters. This visitor is ancient. Not ancient in the way we usually think about age. Not ancient in the way we might describe a rock from our own solar system formed alongside the sun billions of years ago. No, this object, this wandering chunk of ice and dust, may be far older than our solar system itself. 10 billion years old, possibly older. Think about that for a moment. 10 billion years, 10 billion. Where did it come from? This is the question that opens a door into mystery. The comet approached from the direction of Sagittarius, the region where the central core of our galaxy rises into the night sky for millions of years, possibly billions. It drifted through the void of interstellar space, untethered to any star, floating in absolute darkness, a wanderer, a nomad of the cosmos. But it wasn't always alone. Once it had a home. In some other star system, circling some distant sun, 3I Atlas formed alongside other icy bodies in the early days of that system. Planetesimals, they call them, the building blocks of worlds, rock and ice, gradually accumulating through cosmic dust and debris. Then something happened, a catastrophic encounter perhaps, a gravitational instability, a collision, some force, some ancient upheaval wrenched this object from its parent system and hurled it into interstellar space, into the emptiness, into exile. The comet didn't choose this path. It was cast out, ejected, and it has been travelling ever since for eons beyond counting, until, by some statistical improbability, it drifted toward our corner of the galaxy. This is important. Let this sink in. The odds of an interstellar object passing through a solar system are extraordinarily small. The solar system is vast, but space is incomprehensibly vaster. We exist in scattered islands of gravity in an ocean of nothing, and yet, here this object is approaching Mars, approaching the Sun, approaching us, approaching. That word carries weight now. When the comet was first detected by the Atlas telescope, it was already travelling at approximately 137,000 miles per hour, 221,000 kilometers per hour, 61 kilometers per second, travelling so fast that the Sun's gravity will never capture it. It cannot be trapped here. It cannot become part of our solar system. It will pass through, and then it will leave, never to return. A visitor with a fixed departure date. But as it approaches the Sun, as it plunges deeper into the inner solar system, it will accelerate even further. The Sun will pull it faster and faster, and something will begin to happen. Something that transforms this frozen wanderer into something far more visible, far more active, far more strange. For billions of years, 3I Atlas was silent, dark, dormant, an inert chunk of comet material, barely distinguishable from the surrounding darkness, except for the faint starlight reflecting off its icy surface. Then the Sun found it. As 3I Atlas plunged into the inner regions of the solar system, approaching Mars, approaching the Sun, the radiation and heat began to assault its ancient surface, and the comet, in response, began to awaken. This is where things start to get strange. Unlike the first known interstellar object, Oumuamua, which passed through our solar system in 2017, 3I Atlas is active. It's not a dead, inert rock. It's alive with cometary activity. Around its solid nucleus, a coma has formed. A coma is not part of the comet itself. Rather, it's a halo of gas and dust, thousands of kilometers across, that surrounds the nucleus as the comet approaches the Sun. Think of the coma as the comet's breath, its exhalation. As heat from the Sun strikes the icy surface, volatile materials sublimate. They transform directly from ice to gas, skipping the liquid phase entirely. This gas carries dust and debris with it. It streams away from the nucleus, catching starlight, becoming visible. It creates that characteristic tail that comets are famous for, though the tail isn't what you might imagine from children's books. It's wispy, diffuse, barely visible except to sensitive instruments and modern telescopes. Hubble Space Telescope captured images of 3I Atlas on July 21, 2025, just weeks after its discovery. What the images showed was remarkable, a teardrop-shaped cocoon of dust emanating from the nucleus. Not yet spectacular, not yet the dramatic image people conjure when they think of comets, but undeniably there, undeniably active, and it's been growing more active. By early August 2025, research teams monitoring the comet with the James Webb Space Telescope, humanity's most advanced space observatory, had begun to detect something profound in the comet's emissions. Webb's infrared spectrograph was breaking down the light coming from 3I Atlas into its component wavelengths, revealing what elements were being released. Water. Vast quantities of water. Not just a little water, not a modest amount. Data indicated that the comet was losing water, sublimating, vaporizing, streaming away into space at rates so prodigious that one researcher famously described it, using an unexpected metaphor, like a fire hose on full blast, like a fire hose on full blast. This phrasing, though colourful, communicates something essential about what's happening. The comet isn't trickling water into space, it's hemorrhaging it, it's pouring it out. The closer it gets to the Sun, the more violent this outgassing will become. Now here's where it gets complicated. Astronomers have been trying to determine exactly how large 3I Atlas is, and the answer is uncertain. From images captured by Hubble Space Telescope as of August 20th, 2025, the comet's nucleus, the solid core, the actual object beneath all that dust and gas, is not less than 1,444 feet across. 440 meters. That's roughly the length of 4.5 football fields. But it's not more than 3.5 miles across. 5.6 kilometers. That's the upper limit. So the nucleus could be 440 meters across, or it could be 5,600 meters across, or anything in between. That's a range of uncertainty that spans a factor of more than 10. In other words, 3I Atlas could be over 100 times larger than the lower estimate, or much smaller than the upper one. Why doesn't anyone know for certain? Because determining size from distance is deceptively difficult. Telescopes cannot simply measure an object the way a ruler measures a table. Telescopes collect light, they create images, and the brightness of an image depends on multiple factors, not just size, but also the object's reflectivity, its surface composition, the amount of dust surrounding it, the way light scatters through that surrounding material. The coma, that halo of gas and dust, obscures the nucleus. It's like trying to see a candle flame through fog. The fog glows, so you know there's something there, but determining the exact size of the flame becomes guesswork. Estimation, probability. Astronomers are working with what they call upper and lower bounds. The nucleus must be bigger than this. It must be smaller than that, but the exact size remains a mystery. This uncertainty matters more than it might initially seem. Size tells us about the comet's mass. Mass tells us about its density, whether it's a solid, relatively compact object, or a loose collection of rubble barely held together by its own gravity. Density reveals hints about the comet's composition and structure, whether it has a solid core or whether it's more like a cosmic dust ball, and all of these characteristics might help answer a deeper question. Where, exactly, did this object come from? What star system is 3I Atlas's birthplace? We don't know. The trajectory can tell us the direction from which it came, Sagittarius, toward the galactic center, but not which specific star system ejected it. The solar neighborhood contains billions of stars. Finding one particular star and determining whether 3I Atlas originated there would require detailed kinematic analysis, precise measurements of the comet's velocity, and calculations about the positions of nearby stars billions of years in the past. It's possible, though difficult. Researchers are working on it, but for now, the comet's true origin remains a secret held by the Milky Way itself. Here's something that fundamentally separates 3I Atlas from our own solar system comets. Here's something that makes it alien in the truest sense. Every planet, every asteroid, every comet that belongs to our solar system follows what mathematicians call an elliptical orbit. An ellipse is a closed path, a loop. Objects trace out this loop around the Sun repeatedly, returning to the same place again and again. Earth traces an ellipse. Mercury traces an ellipse. The Oort cloud comets, those icy bodies that originate from the outer reaches of our own system and occasionally fall toward the Sun, trace ellipses. They will return. They always return. But 3I Atlas doesn't follow an ellipse. It follows a hyperbola. A hyperbola is an open curve. It's not a closed loop. An object on a hyperbolic trajectory approaches a central point, in this case, the Sun, passes that point, and then continues away, forever. It will never return. The geometry is inexorable. Mathematics allows no other possibility. This distinction is how astronomers determine that 3I Atlas is genuinely interstellar. This is proof that it didn't originate in our solar system. If you reverse the comet's trajectory, running the clock backward through time, the path leads outward, away from our Sun, away from our solar system, into the depths of interstellar space. When 3I Atlas reaches its closest point to the Sun, it's perihelion. That moment will occur around October 30th, 2025. At that time, the comet will be approximately 1.4 astronomical units away from the Sun. 1 AU is the distance from Earth to the Sun, about 93 million miles, or 150 million kilometers. 1.4 AU means 3I Atlas will pass just inside the orbit of Mars, but to Mars, even this will not be particularly close. Mars orbits at a distance of about 1.5 AU. On October 3rd, 2025, Just 4 weeks before the comet's closest approach to the Sun, 3I Atlas will pass Mars. At that moment, the comet will be approximately 30 million kilometers away from Mars. That's about 19 million miles, a cosmic near miss by any reasonable standard. Mars's various orbiters and rovers will have the opportunity to observe this ancient visitor. Multiple spacecraft stationed around Mars have trained their instruments on the comet. It's a rare opportunity. These spacecraft were designed for Mars observation, not for comet studies. Yet now they serve a dual purpose. They've become instruments of a grander scientific curiosity. To Earth, this comet will come no closer than 1.8 astronomical units, 170 million miles, 270 million kilometers, more than the distance from Earth to the Sun. 3I Atlas poses no threat to us, no danger of collision, no threat to our planet, our atmosphere, our existence. We are safe. But safety and distance create a paradox. From a scientific perspective, we wish the comet were closer. Closer observations yield more data. More data yields more understanding. Yet from the perspective of human survival, distance is our salvation. After October 30th, as 3I Atlas swings around the Sun and begins its exit from the inner solar system, it will pass behind the Sun, becoming invisible to Earth-based telescopes. By December 2025, it will emerge on the other side, visible once more. But then it will continue its outbound journey. In March 2026, it will pass Jupiter, and then, slowly, it will recede into the darkness from which it came. It will eventually leave our solar system. It will return to interstellar space. It will become, once again, a wanderer in the vast emptiness. Another ancient object drifting alone between the stars. This is certain. The mathematics permits no other outcome. By August 2025, just weeks after the comet's discovery, an international coalition of astronomers and observatories had begun a coordinated observation campaign. This object was too rare, too significant to be left to isolated observations. Virtually every major space telescope turned toward 3I Atlas. Virtually every Earth-based observatory of sufficient power aimed at the approaching visitor. Hubble Space Telescope captured detailed images showing the teardrop-shaped coma mentioned earlier. Webb's infrared spectrograph began breaking down the comet's emissions into individual elements and compounds. SphereX, a space telescope designed to study the history of the universe, turned its instruments toward this ancient object, adding its observations to the growing archive. Mars orbiters and rovers added their data. Ground-based telescopes from observatories around the world contributed their measurements and spectra. One constellation of findings emerged with particular clarity. The comet's composition is, by certain measures, quite similar to the icy bodies that formed our own solar system in its infancy. Water ice, dust, organic compounds possibly. These are the components of primitive comets. These are the building blocks of planets. They're also, provocatively, potential carriers of the molecular precursors to life, though this is speculation, not established fact. But here's what makes 3I Atlas remarkable. It represents a sample from an entirely different star system, an entirely different planetary formation process. When Comet 3I Atlas formed, orbiting some distant star in some far corner of the galaxy, the processes at work were fundamentally the same as those that created our own solar system's comets. Chemistry is universal. Physics is universal. The laws that govern the universe are the same everywhere. Yet the details, the specific ratios of elements, the particular organic compounds present, the particular characteristics of the dust, these details reveal variations. Variations that tell stories. Stories about different stars, different planetary systems, different epochs of cosmic time. By August 2025, studies had already begun, comparing the comet's properties to those of other known interstellar objects and to the comets of our own solar system. The work is ongoing. The data is still being analysed. Peer review is happening. Published papers are appearing. The scientific community is engaged in an intense collaborative effort to extract every possible piece of information from this visitor. One research team reported a striking observation. The comet's coma had become redder throughout July 2025. The color was shifting. This indicates an evolving surface or coma composition as the comet's activity intensifies. The comet is changing. It's transforming as the sun's heat and radiation assault its ancient surface. This is significant. It suggests that different materials are being exposed as the outer layers sublimate away. Deeper, possibly more pristine material is being revealed. The comet is literally unveiling its history as it approaches its doom. Now, we arrive at one of the most profound questions this comet has raised. How old is 3I Atlas? When did it form? Current evidence suggests that 3I Atlas may be approximately 10 billion years old. 10 billion. Let's place that in context. Our solar system formed approximately 4.6 billion years ago. The sun ignited. The planets accreted from dust and debris. Life emerged on Earth perhaps within a few 100 million years of the solar system's formation. Humans appeared just a few 100,000 years ago. But 3I Atlas's formation occurred roughly twice as far in the past as our solar system's formation. In galactic terms, this places the comet's birth in the early universe, in an era when galaxies themselves were younger, when stars were forming at tremendous rates, when the universe was more chaotic and dynamic than it is today. This is not yet confirmed with absolute certainty. This is an hypothesis based on models of cometary evolution and orbital dynamics. But if true, if 3I Atlas is indeed a 10 billion-year-old relic, then it represents something extraordinary, a material time capsule, a physical messenger from an earlier age of the universe. The implications are staggering. This object has witnessed 10 billion years of cosmic history. It has circled through its parent star system. It has been ejected. It has drifted through the galaxy, watching as stellar processes played out around it. New stars were born. Old stars died in supernovae. The galaxy continued its slow, majestic rotation. And now, after eons of absolute silence and isolation, it has arrived at our solar system, an ancient artifact delivered to our doorstep by the mechanics of orbital dynamics. Or is it something more? Is it a message? A signal? No. This is where we must be careful. This is where speculation must yield to evidence and to healthy scientific skepticism. There is no evidence, none, that 3I Atlas is anything other than what it appears. A comet, an icy object, a product of natural cosmic processes, not of intelligent design or technological construction. And yet the question itself, raised in some circles, reveals something important about human psychology. When confronted with the radically foreign, with the deeply strange, we sometimes struggle not to impose meaning, not to see intention, not to read consciousness into what may be entirely mechanical, entirely natural, entirely explicable through conventional physics. This struggle is part of our humanity, but it is also a cognitive bias that science must vigilantly guard against. By late August 2025, as the scientific community worked methodically through the observational data, another voice entered the conversation, a voice from the fringes of mainstream discourse, a voice that, while originating from academic credentials, carried ideas that diverged sharply from conventional interpretation. Some researchers, citing the object's unusual characteristics, its high water loss rate, its potential antiquity, its apparent cometary nature despite originating from interstellar space, began to propose alternative hypotheses, not mainstream hypotheses, not hypotheses supported by the bulk of observational evidence, but hypotheses nonetheless. One such hypothesis suggests that we might place a certain probability on the possibility that 3I Atlas could be something other than a natural comet. Could it be a technological construct? Could it be an artifact of an advanced civilization? Could it be, in effect, a spacecraft? The reasoning, briefly summarized, goes as follows. An advanced civilization, seeking to explore the galaxy, might construct small, automated probes. These probes might be designed to replicate themselves using the materials found in different star systems. They might migrate from system to system, gradually spreading throughout the galaxy. They might be disguised to appear natural, as comets, asteroids, whatever forms would attract minimal attention. 3I Atlas, under this hypothesis, might be such a probe, or a mothership of such probes. It might carry within it miniaturized technological devices capable of being released into space or into planetary atmospheres, where they might replicate and spread. Now, let's be clear about something. This hypothesis is not supported by the scientific evidence. It is not the mainstream view. It is not what the observational data suggests or indicates. The vast majority of astronomers studying 3I Atlas classify it straightforwardly as a natural interstellar comet, with all the implications that such a classification carries. But the fact that this hypothesis has been raised, that it's being discussed in certain circles, reveals something profound about human curiosity, about our desperate desire to find evidence of other intelligence in the universe, about our anxiety regarding the possibility of contact with beings or entities far beyond our understanding or control. The hypothesis remains speculative, highly speculative, bordering on the realm of science fiction. But it exists in the space between the factual and the fantastic, a space where human imagination, informed by scientific concepts, but not constrained by rigorous evidence, is permitted to roam. This space is not without value. It can stimulate thought, it can push the boundaries of accepted thinking, but it is also treacherous. It is a space where cognitive biases can flourish, where coincidence can be mistaken for pattern, where natural phenomena can be reinterpreted as artificial. The comet's water loss, for instance, dramatic though it is, can be fully explained through conventional cometary physics. The heating of an icy nucleus by solar radiation, the sublimation of volatile materials, the formation of an expanding coma. These are processes astronomers have observed in countless comets throughout history. Similarly, the comet's apparent antiquity, if confirmed, would be extraordinary, but not inexplicable. Cometary objects of great age would naturally be more abundant than younger objects, simply due to the vast timescales involved. The universe is old. It contains objects from many different eras. None of this conclusively rules out the alternative hypothesis, but it does illustrate how natural processes, when unfamiliar or surprising to human observers, can sometimes be reinterpreted through the lens of the extraordinary. And so we return to fundamentals, to the core questions that remain unanswered despite weeks of intensive observation and study. Where did 3I Atlas truly originate? Which star system was its birthplace? Those questions remain shrouded in uncertainty. The comet's trajectory points back toward the galactic center, toward Sagittarius, but billions of stars reside in that direction. Determining which specific star ejected this comet, if such a determination is even possible, would require analysis far more sophisticated than anything currently available. How old exactly is 3I Atlas? 10 billion years is an estimate based on models and assumptions. Precise dating would require techniques and knowledge we don't yet possess. The true age might be 9 billion years, or 11 billion, or something else entirely. What is the true diameter of the nucleus? We know it's between 440 meters and 5.6 kilometers. But which of these bounds represents the actual size? The answer depends on factors: reflectivity, dust distribution, surface composition, that are themselves incompletely understood. What compounds make up the comet? Water, certainly. But what else? Organic molecules? Carbon monoxide? Nitrogen? Ammonia? Researchers continue analyzing spectroscopic data, but the picture remains incomplete. Different studies sometimes reach different conclusions based on how the data is interpreted. Will the comet break apart as it approaches the Sun? Some comets survive their passages through the inner solar system intact. Others fragment, splitting into multiple pieces. Will 3I Atlas remain whole, or will it become a constellation of debris? The answer depends on its structural integrity, on how densely packed it is, how strong its internal cohesion is, and those properties are, at present, unknown. These unknowns create a peculiar tension. On one hand, science has provided an enormous amount of information about 3I Atlas in a remarkably short time frame. Within weeks of discovery, we knew its trajectory, its composition, its origin from outside our solar system, the date of its closest approach to the Sun, and many other details. On the other hand, the most fundamental facts, the facts that would allow us to truly understand this object, to fit it into our models of comet formation and evolution and interstellar dynamics, remain elusive. And here, in this gap between knowledge and ignorance, in this space where facts give way to questions, is where mystery resides. This is where human curiosity finds purchase. This is where the imagination becomes engaged. October 3rd, 2025. A date circled on calendars, a date marked in mission control centers, a date when something extraordinary will unfold. On that date, 3I Atlas will pass within 30 million kilometers of Mars, 19 million miles, closer than it will come to Earth, relatively speaking. And Mars is not empty. Mars is not uninhabited by human observation. Multiple spacecraft currently orbit Mars. Mars Express, from the European Space Agency, surveys the planet's atmosphere and geology. ExoMars Trace Gas Orbiter, also from ESA, specializes in detecting atmospheric compounds. Additional rovers on the Martian surface, Perseverance, Curiosity, conduct ground-level investigations. Various deep space missions are currently in transit or positioned to conduct observations. All of these assets have been, or are being, directed toward 3I Atlas as it approaches Mars. This comet, this ancient visitor, will be observed by more sophisticated instruments than any previous interstellar object during such an encounter. What will they detect? Images of the coma, certainly. Spectroscopic data revealing what elements are being sublimated and released into space. Measurements of the comet's brightness and reflectivity at multiple wavelengths. Potentially the first close observations of a truly hyperbolic interloper in our solar system. This data will be extraordinarily valuable. It will refine estimates of the comet's size, composition, and structure. It will provide clues about the parent star system from which 3I Atlas originated. It will inform models of cometary evolution and the nature of interstellar objects. But beyond the scientific utility lies something more fundamental. The sheer act of observation itself. The moment when multiple independent observers, using different instruments, different vantage points, different methodologies, all focus their attention on a single, unified target. It is a moment of consensus, a moment of unity in the face of cosmic mystery. And in that moment, humanity, divided though it may be in so many ways, becomes united in curiosity, in the desire to understand, to learn, to expand the boundaries of knowledge. This is what brings observers to telescopes in the dead of night. This is what motivates the construction of billion-dollar space observatories. This is what drives the scientific enterprise itself, the fundamental human hunger to comprehend the universe. 3I Atlas, by arriving when and where it did, has provided humanity with a gift, an opportunity to practice this fundamental activity of understanding on a rare and remarkable object. October 2025. The comet accelerates. The sun's gravity intensifies its pull. Day by day, the object that has drifted dormant through the void for billions of years picks up speed, plunges deeper into the inner solar system, and transforms from a barely perceptible speck into something increasingly substantial. By early October, with Mars already behind it and receding into the distance, 3I Atlas enters the zone where its encounter with the Sun becomes imminent. The coma expands, the outgassing intensifies. Water and other volatile materials stream away from the nucleus with escalating force. From telescopes on Earth, the comet becomes brighter, more visible, more undeniable. On October 3rd, as mentioned, the comet passes Mars, but it does not linger. It continues its inbound trajectory toward the Sun. The solar radiation intensifies. The heating becomes more severe. The comet's surface, already melting and sublimating, becomes a landscape of extreme geological transformation. What happens to such an object under these conditions? The comet's surface is a mosaic of ice and rock and organic compounds. As the sun's radiation heats it, the ices don't simply melt, they turn directly to vapor. This sublimation is violent, explosive in cosmic terms. Jets of gas erupt from the surface, carrying dust with them. These jets create a dynamic, chaotic environment around the nucleus. The nucleus itself, that solid core ranging from 440 meters to 5.6 kilometers across, begins to experience tremendous structural stress. On one side, facing the sun, temperatures soar. On the opposite side, facing away, the temperature remains close to the temperature of interstellar space, minus 270 degrees Celsius. The temperature differential creates immense mechanical stress within the structure. There is a real possibility, not certainty, but a genuine possibility, that the comet will fragment, that it will break apart into multiple pieces. This fragmentation, should it occur, would scatter what remains of 3I Atlas across a wider region of space. The multiple fragments would continue on their hyperbolic trajectories, diverging from one another, eventually leaving the solar system as a constellation of smaller objects rather than as a single coherent mass. Or it might hold together. Some comets survive their solar passages largely intact. The nucleus, held together by gravitational self-attraction and internal cohesion, might weather the heat and stress and continue onward as a diminished but continuous object. Neither outcome is certain. Both are possible. October 30th arrives. 3I Atlas reaches perihelion, its closest approach to the Sun. At approximately 1.4 astronomical units, it passes through the inner solar system, closer to the Sun than Mars but still far from Earth. The coma at this point may have expanded to enormous proportions. If there is a visible tail, it may stretch across millions of kilometers of space. A spectacular display for those with the proper instruments and the opportunity to observe. Yet here's something poignant about this moment. If the comet has fragmented, if it broke apart in the preceding days or weeks, then the encounter with the Sun might be entirely chaotic. Multiple pieces, each following its own trajectory, each sublimating independently, each responding to the solar wind and radiation pressure in slightly different ways. The perihelion passage would no longer be a single event, but a distributed phenomenon, a cascade of events playing out across weeks. This is not unprecedented. In 1992, a comet named Shoemaker-Levy 9 famously fragmented before crashing into Jupiter. In 2020, another comet underwent a dramatic fragmentation that astronomers observed in real time. These events are rare, but they happen, and they remind us that comets, despite their reputation for permanence and predictability, are fragile objects, precarious, subject to destruction by the very forces that give the solar system its structure and character. Will 3I Atlas fragment? As of late August 2025, no definitive signs of fragmentation had been observed. The comet appeared to remain intact, but the encounter with the Sun is still ahead. The heating is still escalating. The possibility remains real. This uncertainty adds an element of genuine suspense to the comet's continued approach. Astronomers will be monitoring carefully. Every image, every spectrum will be scrutinized for signs of structural degradation or change. And if fragmentation occurs, if the comet breaks apart, the event will be documented in extraordinary detail. It will provide invaluable data about cometary composition and structure, data that can only be gathered by observing a comet actually undergoing destruction. By late October, 3I Atlas disappears behind the Sun. From Earth's perspective, the comet vanishes. It passes behind the solar disk, invisible, unreachable. The ground-based telescopes lose sight of it. The space telescopes in solar orbit can still observe it, in some cases. But for observers on Earth, the comet becomes inaccessible. This disappearance lasts approximately 6 weeks. 6 weeks of silence, 6 weeks when astronomers must rely on historical data, on models, on calculations about what might be happening on the far side of the Sun. Then, in early December 2025, the comet re-emerges. It appears on the opposite side of the Sun from where it disappeared. Its trajectory carries it out of the solar glare and back into regions of space where it becomes visible once more. The coma reappears in the telescope's fields of view. The nucleus, though diminished by its passage through the inner solar system, continues its journey outbound. The comet will have changed. The intense heating, the sublimation, the bombardment of solar radiation, all of these will have altered the object. It will be somewhat smaller than when it arrived at perihelion. It will have lost mass in the form of outgassed water and other volatiles. Its surface will be transformed. New ices previously buried beneath the exterior may now be exposed. The December emergence provides an opportunity for the second phase of observations. The comet is heading away from the Sun now, so the outgassing will gradually slow and diminish. The coma will begin to dissipate. The tail, if there is one, will begin to fade. The comet will return to a dimmer, less spectacular state as it resumes its journey into the darkness from which it came. But December observations are crucial. They provide data about the comet's condition after its perihelion passage. They allow astronomers to assess how much mass was lost. They reveal the characteristics of the newly exposed surface materials. They complete the picture of the comet's evolution throughout its entire solar system encounter. By early 2026, 3I Atlas will have passed beyond Jupiter. The comet will be in its outbound trajectory now, slowly receding from the Sun, retreating into the cold outer regions of the solar system and beyond. From ground-based telescopes on Earth, it will gradually fade. It will become dimmer, dimmer, dimmer. Eventually, even the most powerful Earth-based observatories will lose it. Only the space telescopes, potentially, will retain observations as the comet recedes further and further, but even the space telescopes will eventually lose it. The comet will become too distant, too dim, too insignificant from any perspective within our solar system. It will return to invisibility. It will continue its outbound journey, retreating into interstellar space, heading back to the darkness from which it came. This time, it will truly be leaving. It will never return. The hyperbolic trajectory permits no other possibility. 3I Atlas will travel through the galaxy now, perhaps for billions of years, until it eventually approaches another star system. Perhaps it will encounter alien astronomers who will detect it as it drifts past. Perhaps it will pass through stellar systems uninhabited, unobserved, unmissed, or perhaps the solar system it encounters will be the next place where it settles, where a gravitational interaction with planets or a stellar passage captures it into an elliptical orbit. At that point, it would become part of that system, as it once was part of some distant star system billions of years ago. The cosmic cycle continues. Objects cycle through star systems. They are ejected. They drift. They arrive elsewhere. The universe, on geological timescales and beyond, is constantly redistributing its materials, its building blocks, its ancient fragments. By December 2025, with months of observational data accumulated from multiple space telescopes and Earth-based observatories, research teams had begun publishing preliminary findings. Preprints appeared on scientific archives. Papers were submitted to peer-reviewed journals. The collaborative effort to understand 3I Atlas was producing results. What have these studies revealed about the comet's composition? The most certain finding: water. Vast quantities of water ice constitute a significant portion of the comet's structure. This is confirmed by multiple independent observations, particularly from the James Webb Space Telescope's infrared spectrograph, which can identify the chemical signatures of water ice even across hundreds of millions of kilometers of distance. The presence of water ice is, in some respects, unremarkable. Water ice is common in comets, but the rate at which 3I Atlas has been losing water, the rate at which it has been sublimating into vapor, is unusual. Some researchers describe it as unusual. Others describe it as exceptional. The terminology matters less than the underlying fact. The water loss rate exceeds what might be predicted based on models of comets in our own solar system. Why? Multiple explanations are possible. The comet might be structurally different, more porous, more loosely bound, than typical solar system comets. Porosity would increase surface area, increase the rate of sublimation. Or the comet might be experiencing more intense solar heating than models predicted. Or the composition of the comet's surface might be such that certain materials sublime away, exposing fresh, volatile ice beneath. This cascading exposure would amplify the outgassing rate. All of these explanations remain speculative. They are hypotheses awaiting confirmation through additional data. Beyond water, spectroscopic analysis has suggested the presence of carbon monoxide and carbon dioxide. These are also typical cometary ices. Carbon monoxide is interesting because it sublimates at even lower temperatures than water. It remains frozen in interstellar space, but begins to vaporize more readily as the comet approaches the Sun. The presence of carbon dioxide similarly indicates the preservation of volatile materials from the comet's original formation in its parent star system. Organic compounds, complex carbon-based molecules containing hydrogen, nitrogen, oxygen, are more difficult to detect from a distance, but Webb observations have provided tantalizing hints of their presence. The infrared signatures picked up by the telescope's spectrograph suggest patterns consistent with various organic molecules. But identification of specific compounds remains tentative. The data is suggestive but not definitive. This is where speculation becomes permissible, though it must be carefully hedged with caveats. If 3I Atlas contains significant quantities of organic compounds, complex molecules that could serve as precursors to amino acids or other biochemical building blocks, then it carries within it something profound. Evidence that the chemistry of life's origins is not unique to Earth. It is not specific to our solar system. It is part of the basic chemistry of the universe itself. Amino acids have been detected in some meteorites, in some comets. The building blocks of proteins, the molecules that form the physical basis of all known life, are apparently widespread throughout the cosmos. If 3I Atlas contains these compounds, then it is not merely a chunk of ancient ice and rock. It is a repository of information about the chemistry that, somewhere, might give rise to life. But again, this is speculation layered upon measurement. It is suggestion, not certainty. The spectroscopic data hints at the presence of organic compounds, but the exact identity and quantity of these compounds remain unclear. Where did 3I Atlas come from? This question has driven much of the research following the comet's discovery. It is a question that yields not one answer, but multiple possible answers. One leading theory: 3I Atlas originated in a planetary system orbiting a star in the inner galaxy. The inner galaxy, closer to the galactic center, is denser than the outer regions, like the spiral arm where our solar system resides. In this denser region, gravitational interactions between stars are more common. Planetary systems are more frequently disrupted. Comets and planetesimals are more often ejected from their parent systems. If 3I Atlas originated in such a system, it would have been one of billions of objects formed alongside planets. Over the course of its existence, over hundreds of millions or billions of years, it would have been perturbed by stellar encounters, by gravitational perturbations from passing stars, by the general chaos of the galactic environment. Eventually, one such encounter would have provided the impulse to eject it into interstellar space. Once ejected, the comet would have drifted through the galaxy. For billions of years, it would have traveled through the dark, interacting with nothing, observing nothing, if observation is even a meaningful term for a lifeless object. It would have been ancient, solitary, utterly alone. Then, by chance, astronomical chance, statistical chance, the vast improbability that somehow manifests across billions of years, it drifted close enough to our solar system's gravitational field to be captured into its trajectory, not captured permanently, not captured into an orbit that would hold it, but captured into a trajectory that passes through the solar system's inner regions. This is the mainstream theory. It is supported by the observational data. It requires no extraordinary assumptions. It relies entirely on known processes: stellar formation, planetary formation, gravitational perturbations, orbital dynamics. All of these are well understood. They have been observed in other systems. They are not controversial, yet within this mainstream framework, questions remain. What star system was the comet's birthplace? The trajectory points back toward Sagittarius, toward the galactic center. But this is a direction, not a destination. Billions of stars reside in that direction. Determining which specific star ejected 3I Atlas would require either A. Precise measurements of its velocity in multiple dimensions, allowing back calculation to determine which stars it might have passed billions of years ago, or B. Direct observation of similar objects orbiting nearby stars, allowing comparison of composition and characteristics. Neither approach has yet yielded definitive results. Research is ongoing, but for now, the comet's specific origin remains a mystery. Another possibility, less mainstream but not impossible, 3I Atlas originated in a planetary system closer to our region of the galaxy, but was ejected relatively recently, perhaps only millions of years ago, rather than billions. Under this scenario, the comet would have traveled through interstellar space for a shorter period, arriving at our solar system more recently. The evidence for or against this scenario is ambiguous. The comet's composition doesn't tell us its age definitively. Physical processes in space occur slowly, but over millions of years, they would leave distinctive marks on a cometary object. Surface weathering, chemical changes, cosmic ray damage to exposed ice. These factors could, in principle, be detected and used to constrain the comet's age, but the current observational data is insufficient to make such determinations with confidence. This remains a hypothesis, not yet falsifiable or confirmable with the data currently available. And then, there are the speculative theories that venture further from the mainstream. Theories suggesting that 3I Atlas might be a rogue planet, a terrestrial world ejected from a planetary system and now wandering the galaxy. The composition doesn't quite fit this model. Rogue planets should be rocky, not icy, but the theory has been proposed nonetheless. Or theories suggesting that 3I Atlas might be an artifact of technological origin, constructed by an advanced civilization, disguised as a natural object. This theory, as discussed earlier, has no evidence supporting it. It relies entirely on speculation and on the notion that we should consider all possibilities, no matter how improbable. This proliferation of theories, from the rigorously supported to the speculative to the fantastical, reflects something important about how science progresses. It is not a linear march from ignorance to knowledge. Rather, it is a landscape of possibilities. Some possibilities are well supported by evidence. Others are more marginal. Others still lie at the frontier between the scientific and the speculative. The most productive scientists learn to navigate this landscape, to follow the evidence, to propose new hypotheses when data suggests they might be warranted, but also to remain skeptical of extraordinary claims, to demand extraordinary evidence, to insist on rigor and reproducibility before accepting new ideas into the corpus of scientific knowledge. 3I Atlas has provided humanity with an opportunity to practice this kind of thinking on a grand scale. It is a test case for how we approach mystery and the unknown in an era of advanced technology and sophisticated analysis. 3I Atlas is only the third known interstellar object to be observed passing through our solar system. The first was Oumuamua, detected in 2017. The second was 2I Borisov, detected in 2019. Now comes 3I Atlas, detected in 2025. 3 objects in just 8 years. Is this a coincidence? Or does it reflect something about the prevalence of interstellar objects in the galaxy? If we extrapolate from these detections, assuming that our observation capabilities are roughly constant, we can estimate that such objects pass through the solar system at a rate of roughly 1 every few years, not 1 per year, necessarily. But on that timescale, 1 every few years. Now extrapolate further. Across the billions of stars in the galaxy, billions of solar systems exist. If interstellar objects pass through each system at a similar rate, then the total number of such objects currently in transit through the galaxy would be enormous. Trillions, quintillions, more than we can comfortably conceptualize. This is the universe as a vast, dynamic system, objects constantly in motion, constantly transferring between star systems, constantly shuffling materials across the galaxy, comets and asteroids and potentially planets and moons, all in a slow, grand cosmic circulation. This perspective changes how we think about 3i Atlas. It is not unique, it is not extraordinary in the sense of being unprecedented or impossible. It is merely rare from the perspective of a single observer, a single planet, a single civilization, rare from our particular vantage point in space and time. But in the context of the entire galaxy, in the context of billions of years of stellar and cometary evolution, objects like 3i Atlas are presumably common. They are ordinary features of galactic dynamics, even if they are extraordinary from Earth's perspective. This raises a philosophical question. How do we understand the ordinary and the extraordinary? How do we contextualize phenomena that are rare from a local perspective, but commonplace from a cosmic perspective? One answer: we recognize that rarity is scale-dependent. What is rare in a solar system is common in a galaxy. What is common in a galaxy is rare for any individual star system. The perspective matters. The frame of reference matters. Reality itself doesn't change, but our understanding of its significance shifts depending on the scale at which we choose to observe. 3i Atlas has arrived at a moment when humanity's technological capabilities allow us to observe such objects in unprecedented detail. We have Hubble and Webb and Sphere-X and countless ground-based observatories all trained on this ancient visitor. We have the capability to extract vast amounts of data from its light and radiation. We can analyze its composition, its structure, its behavior. Earlier in cosmic history, such objects passed through our solar system undetected. They arrived and departed in silence and darkness, observed by no conscious entity, measured by no instrument, understood by no intelligence. But now, in this particular era, humanity is present. Humanity has developed the technology to observe, and so this comet, ordinary though it may be in galactic terms, has become an object of intense scientific scrutiny. This is a remarkable convergence. The ordinary made extraordinary through the lens of human observation and understanding. Despite months of intensive observation, despite the coordinated efforts of the world's leading observatories and research institutions, fundamental questions about 3i Atlas remain unanswered. The comet's true size is still uncertain, somewhere between 440 meters and 5.6 kilometers, 100 times larger or much smaller. This is not precision. This is a range of possibilities bounded by upper and lower limits. The comet's true composition remains incomplete. Water, carbon monoxide, carbon dioxide confirmed. Organic compounds suggested but not definitively identified. Hundreds of other potential compounds unexamined. We know what the comet contains, but we do not fully understand what it is. The comet's origin remains mysterious. It came from Sagittarius, from the direction of the galactic center. But which star system? Which planetary system? Which catastrophic encounter ejected it? These questions cannot be answered with current data and current methodologies. The comet's age is estimated at roughly 10 billion years, but this is an estimate. It could be older. It could be younger. We are reading the comet's history in its surface features and its composition, but that history is written in a language we only partially understand. And most profoundly, we do not know what this comet represents in the broader cosmic context. Is it a messenger, a warning, a gift, a random object of no particular significance? These are not scientific questions in the strict sense. They are philosophical questions. They concern meaning and significance, not just facts and measurements. But they matter. They matter because how we interpret the cosmos shapes how we understand our place within it. Consider this. 3i Atlas has traveled for billions of years through an unimaginably vast universe. It has witnessed the formation and death of stars. It has passed through regions of space where planets orbited and potentially developed life. It has drifted through epochs of cosmic time, almost incomprehensible in their magnitude, and now, by a statistical improbability, it has arrived at our solar system, at our planet, in our present era, at a moment when conscious beings capable of understanding exist here. Is this coincidence? Obviously, in one sense, it must be. The probability of any specific object arriving at any specific location, at any specific time, is infinitesimal. Probabilities that small, multiplied by enough trials, eventually become certainties. Given enough objects and enough time, the improbable becomes inevitable. And yet there is something that resonates in the human psyche about such coincidences, something that makes us wonder if there is meaning beneath the surface of randomness, something that suggests to us that perhaps the universe is less random than it appears. This is the domain where science and philosophy blur into one another, where measurement and meaning become intertwined, where the objective facts about a comet, its trajectory, its composition, its age, become inseparable from the subjective questions we ask about what it means. By the end of 2025, the era of 3-eye atlases intensive observation will be ending. The comet will have receded beyond Jupiter. It will be dimming. The novelty will be fading. The media attention will move on to other topics, other phenomena, other mysteries. But within the scientific community, the work will continue. Researchers will spend years, potentially decades, analyzing the data collected over these few months. Peer-reviewed papers will be published. Conferences will feature presentations about 3-eye atlas. Graduate students will write dissertations about various aspects of the comet's composition and behavior. The archive of observations, the thousands of images, the millions of spectra, the vast mountains of data will remain. Accessible to researchers around the world, reanalyzed by future scientists using new techniques, new instruments, new methodologies not yet developed. This is the long-term legacy of 3-eye atlas. Not just the immediate discoveries, though those matter, but the establishment of a comprehensive observational record of an interstellar object, a record that will serve future research for decades or centuries to come. And there is another legacy, less tangible, but perhaps more significant. The renewed recognition of humanity's place in the cosmos, the reminder that we are not alone in the universe, that other worlds exist, that materials travel between star systems, that the cosmos is fundamentally interconnected, linked by gravity and radiation, and the slow dance of orbital mechanics across billions of years. 3-eye atlas has provided a physical embodiment of these truths, an actual object from another star system, passing through our solar system, available for observation and study. It is not a hypothesis or a theory, it is a fact, evidence, reality. For students contemplating careers in astronomy or planetary science, the discovery of 3-eye atlas has been a profound gift. Here is a phenomenon that occurred during their educational years. Here is a mystery they might help solve. Here is an opportunity to contribute to humanity's understanding of the cosmos in real time. For the general public, the comet has provided a moment of connection with the broader universe, a reminder that the night sky is not static, that phenomena of cosmic significance are occurring, that we live in an active and dynamic cosmos. This connection is crucial. In an age of increasing technological mediation and digital distraction, moments of genuine contact with the cosmos, moments when one can look up at the night sky and know that an ancient visitor from another star system is passing through space nearby, these moments are precious. They rekindle the sense of wonder that first drew humans to study the stars. 3-eye atlas has been a gift in many ways. As 3-eye atlas recedes from our region of space, a question poses itself. What have we truly learned? The facts are clear. We have observed an interstellar comet. We have measured its trajectory, its composition, its behavior. We have added significantly to our understanding of comets and of the processes by which objects are exchanged between star systems. These are genuine achievements. They represent real progress in human knowledge. But in another sense, the comet remains as mysterious as when it was first discovered. We know more about it, yes. We understand better how it behaves in sunlight, how it sublimates, what elements compose it. We can predict where it will be at any given moment in the future, but we do not know where it came from, not truly, not with certainty. The direction points back toward the galactic center, but billions of stars reside there. Finding its true origin would require knowledge we do not possess. We do not know its age with precision. 10 billion years is an estimate, well-reasoned but still an estimate. It could be significantly older or younger. We do not know what it represents. Is it a common object, one of countless such wanderers transiting through the galaxy at any given moment? Or is it in some sense unique, exceptional? And most fundamentally, we do not know whether this is the last interstellar object we will observe for years, or whether more will arrive in quick succession, revealing that such objects are far more common than we realized. These unknowns are not failures of observation. They reflect, rather, the inherent limitations of our knowledge. We can observe, we can measure, we can analyze. But there are fundamental limits to what we can understand about an object from a distance. To truly understand 3I Atlas, we would need to send a spacecraft to intercept it, to collect samples, to analyze its structure directly rather than through the filter of light and radiation. But 3I Atlas is accelerating away from our solar system even now. Catching up to it would require a spacecraft of extraordinary capability. Such a mission is beyond our current technological reach. It is not impossible. Given sufficient technological advancement and sufficient dedication of resources, such a mission might someday be feasible. But for now, it remains a dream rather than a practical possibility, and so 3I Atlas will carry its secrets with it, into the depths of space, away from our solar system, away from Earth, into regions of the galaxy where no human instruments can follow. This is the tragedy of encountering an object so distant, so ancient, so foreign to our world. We can observe it, we can measure it, we can wonder about it, but we cannot truly know it. Some mysteries will remain forever beyond our reach. There is a peculiar paradox inherent in the progress of science. Phenomena that seem impossible become routine. Mysteries that seem eternal are solved. The unknown gradually, relentlessly, becomes the known. Consider, a century ago, the idea that objects from outside our solar system would pass through it would have seemed absurd. The solar system was conceived as a closed system, isolated, self-contained. The idea of material transfer between star systems was the province of science fiction, not serious science. Then came the observations suggesting that Oumuamua, discovered in 2017, was interstellar. The scientific consensus shifted. The impossible became possible. The impossible became real. 8 years later, the discovery of 3I Atlas merely confirmed what Oumuamua had suggested. Interstellar objects are real. They exist. They pass through star systems. This is not a one-time anomaly. This is a regular feature of galactic dynamics. In another century, as more interstellar objects are discovered and studied, they may become routine, boring even, discovered regularly by automated systems, catalogued, noted, and then largely ignored until some particular object merits special attention. This is the trajectory of science. The dramatic becomes ordinary. The unknown becomes known. The frontier keeps receding, inviting further exploration. But in this present moment, in 2025, 3I Atlas remains something extraordinary. It is a visitor from another world, a messenger from a distant stellar system, a bearer of information about cosmic processes and stellar evolution, and the distribution of materials throughout the galaxy. To observe it is to be reminded of something essential. The universe is far larger, far older, far more complex than any individual human mind can fully comprehend. We are observers of phenomena that vastly exceed our intuitive understanding. We are creatures of a small planet orbiting an ordinary star in the outskirts of a galaxy containing hundreds of billions of stars. The universe extends far beyond our perceptual and cognitive boundaries, and yet, through the application of reason, through the construction of instruments, through the collaborative effort of scientists across generations and disciplines, we can gradually expand the boundaries of our knowledge. We can understand phenomena that lie beyond direct human experience. We can comprehend processes that unfold across billions of years and billions of kilometers. 3i Atlas is a symbol of this expanding knowledge, a demonstration of humanity's capability to observe and understand cosmic phenomena, a reminder that ignorance, while vast, is not total. The boundaries of knowledge retreat, slowly but inexorably, as we ask better questions and develop better tools to answer them. And so, 3i Atlas recedes into the darkness, back toward the outer regions of the solar system, back toward the void of interstellar space, back to the cold, the silence, the vast emptiness from which it came. By March 2026, it will have passed Jupiter. By 2030, it will have traveled beyond the Kuiper Belt, beyond the outermost reaches of our solar system's gravitational influence. From our perspective, it will be gone, lost to observation, a memory more than a present phenomenon. But the comet continues. It continues its journey. It continues its voyage through the galaxy. For billions of years more, it will drift through space, potentially encountering other star systems, other planets, other observers. Perhaps some distant civilization will observe 3i Atlas as it approaches their solar system. Perhaps they will wonder at its origins as we have wondered. Perhaps they will study it with instruments beyond our comprehension, learning from it secrets we could never discern. Or perhaps 3i Atlas will drift forever, unobserved, unmeasured, unknown except by us, a moment of notice in an otherwise eternal journey through darkness. We cannot know. We can only observe and wonder and speculate. What this comet has taught us, above all else, is the importance of staying curious, of asking questions, of looking up at the night sky and genuinely wondering what is out there in a world increasingly dominated by routine and certainty, where algorithms predict what we will like, where information is filtered to match our existing beliefs, where the future seems predetermined by the convergence of technological and social forces. This comet reminds us that the universe is fundamentally strange, fundamentally surprising, fundamentally mysterious. We do not know what tomorrow will bring. We do not know what phenomena might appear in the night sky. We do not know what questions, once asked, might lead us toward new understanding. But we can remain open to these possibilities. We can maintain the intellectual flexibility to be surprised. We can resist the temptation to assume that we already understand the world in all its essentials. This is what it means to think critically. Not merely skepticism, though skepticism has its place, but rather a genuine openness to evidence. A willingness to revise our understanding in light of new data. A recognition that mystery and wonder are not obstacles to understanding, but rather invitations to deeper inquiry. 3i Atlas is such an invitation. It has invited us to observe carefully, to measure precisely, to question our assumptions, to wonder about the cosmos and our place within it. Whether or not this comet originated from an advanced technological civilization, whether or not it carries within it organic compounds from which life might someday emerge, whether or not it represents something more than just another wandering chunk of ice and rock, regardless of the answers to these questions, one thing is certain. 3i Atlas has expanded our understanding of the cosmos. It has shown us that the universe is more complex, more dynamic, more interconnected than we sometimes imagine. It has reminded us that phenomena of profound significance can manifest in our solar system, that we live in an active universe, that observation and curiosity remain our greatest tools for understanding. As this ancient visitor travels back into the void, leaving behind only data and memories and photographs and spectra, we are left with a fundamental truth. The universe is stranger than we know, stranger than we can easily imagine, but not so strange that we cannot study it, not so mysterious that we cannot ask questions and seek answers. 3i Atlas came to us from the darkness. It passed through our solar system. it will return to the darkness. But in those few months of passage, it gave us something irreplaceable, a window into the broader cosmos, a reminder that we are not isolated, a demonstration that the universe is fundamentally interconnected, that materials travel between star systems, that the cosmos is alive with phenomena waiting to be observed and understood. To anyone watching the night sky, searching for this comet during those months of visibility, there is a simple message. Keep looking, keep questioning, keep wondering. The cosmos is far vaster and far stranger than any single lifetime can encompass. But each observation, each question, each moment of genuine curiosity adds to the collective human understanding. It contributes to the grand project of making the unknown known. 3I Atlas will not return. Other comets will. Other interstellar objects will eventually arrive. Perhaps in your lifetime, perhaps long after you have gone. But the universe will continue to send visitors. It will continue to present mysteries. It will continue to invite us to look outward and ask, what is out there? That is the legacy of 3I Atlas. Not just the data it provided, not just the scientific knowledge it contributed, but the renewal of wonder itself, the rekindling of curiosity, the reminder that in a universe this vast, this old, this fundamentally strange, ignorance is not something to be ashamed of. Rather, it is an invitation, an opportunity, a pathway forward. So look up, observe, measure, question, speculate, dream, wonder. The universe is waiting, and it is far stranger, far more beautiful, far more profound than we can ever fully comprehend. 3I Atlas has shown us that. It has reminded us, and for that gift, we can be eternally grateful to this ancient wanderer from beyond our solar system. It came from the stars. It visited our world, and now it returns to the stars, carrying with it our observations, our questions, our hopes, that someday, in some distant age, we might understand the cosmos as it truly is. Until then, we watch, we wait, we wonder, and we remain forever curious.